All right, well, hello everyone, and welcome back. In this video, we will introduce linked lists in C++. You will see that linked lists may be a little bit intimidating at first, but in this video we will learn how to draw pictures and break these linked lists down into simple steps. We'll see that linked lists are an incredibly powerful tool in C++. And they form the building blocks for many powerful data structures that are used throughout programming. So let's go ahead and get started. So here's our goals for today's video. First, we will briefly discuss the advantages and limitations of linked lists. Next, we will learn how to write C++ code to declare and construct linked lists. But in addition to just writing C++ code, we will also learn how to draw pictures. And you might think, well, why would I do that? Isn't that just extra effort? But it turns out that drawing pictures is really important to help visualize what is going on. And once you get comfortable drawing pictures and visualizing linked lists, you'll see that the pictures really help. So I highly recommend that as you watch our video today, have pen and paper in hand as we go through our examples. And you'll see that drawing pictures really helps, especially when you're first starting out. Eventually, you may become skilled enough that you don't need to draw pictures anymore, and you'll see that in some of our assignments, it might even be required because it's so important. So definitely follow along with our examples, and you'll see how drawing pictures will really help make linked lists a lot easier to learn. Finally, we will start using what's called the arrow operator to help us manipulate linked lists. So let's go ahead and get started. All right, so let's first ask ourselves, why do we need additional tools like linked lists for our programs? Well, let's first take a moment and revisit this idea of what's called data structures. Remember, a very important problem in engineering and in programming is figuring out the best way to store and manipulate our data. And so far in the course, we've learned about several tools, including arrays, vectors, and structs. And these are all very useful tools. But what happens if we need to insert or delete something part way into our list? Or what happens if we need to add something to the front of our list of data? Think about the undo function on a keyboard. That will basically take the thing that we did most recently and undo it. And as nice as arrays, vectors, and structs are, arrays, vectors, and structs are not as useful if we want to insert or delete data partway through. I mean, we certainly can do insertion, but it's a little bit more effort because we'd have to write extra functions and extra code. So arrays, vectors, and structs are not necessarily as useful when we need to insert things. In the front or middle of our list. And so this is where linked lists come in. This is not to say linked lists are better than arrays, vectors, and structs, but simply that linked lists are another tool in our toolbox. And depending on what we need to do for a specific application, sometimes linked lists are a really great tool. Other times we're better off using an array, a vector, or a struct. So part of being a programmer is recognizing when's the right time to use each tool in our toolbox. So let's talk a little bit more about the specific differences between linked lists and other types of data structures like arrays or vectors. So an interesting feature of linked lists is that they are created in the dynamic memory. And what this means is, since we've created it in the dynamic memory, linked lists can grow and shrink as needed while our program is running. Remember, this is different than for arrays. Remember, typically we need to declare the size of our array ahead of time. Another advantage of linked lists is that they're built using pointers. And so it's actually fairly easy to insert a node between other nodes of our list. For example, if we have a linked list like shown below, we have all these nodes that are connected with pointers. So it's actually pretty easy to change the contents of our linked list simply by changing what our pointers point to. For example, if we wanted to insert this node into our list, notice we would just need to update our pointers. Or if I wanted to insert something else right here, I could take my node and insert it in, just like this. So when we need to make different kinds of data in our programs, and we need to be able to quickly and easily insert and remove items, a linked list could be a lot more flexible of an option. We want to be the good kind of lazy, we want to be efficient, and so for some applications, linked lists are a really important tool. If you take more advanced programming courses, you will also see that these sort of node-based structures that we create with linked lists, these can actually be used to make more advanced data structures like trees as well. So when would we want to use a linked list instead of something like an array or a different kind of data structure? So linked lists are very useful to store data if you know that you need to insert items at the beginning or in the middle of your list. Or in cases where your data needs to be able to grow and shrink as needed. Also, if you want to use dynamic memory, linked lists are a very good option. But remember, every tool has its advantages and disadvantages. In the case of linked lists, their big disadvantage is that linked lists are not as efficient if we want to access a particular element in our list. Because the disadvantage of linked lists is that we have all these nodes connected by pointers. So if I want to access my third node in my linked list, the only way I can access that item is by starting at the head pointer of my linked list and walking through my list until I reach the node that I want. I am not able to directly jump to node 3, or whichever node I'm looking for. I have to step through my entire list. And you might imagine if I've got millions of items in my linked list, it could take a long time for me to step through the entire list and find the thing I'm looking for. And so that's one advantage where arrays, for example, can be more efficient because you can use indexing to directly jump to the item in the memory that you're looking for. All right, so once again, why do we bother to learn about linked lists in this class? Well, one main reason is because they're another important tool in our toolbox. They help us do more things with our data. And as we mentioned, it's especially helpful when we need to insert or delete things from our list. And notice it's very easy to add things to the front, middle, or back. And the lists live in dynamic memory. Also, if you happen to be a computer science, computer engineering, or even electrical engineering major, you're probably going to take an entire course on data structures. And you'll most likely also take some sort of algorithms course. And in both of those more advanced courses, you are absolutely going to need to use pointers and linked lists as the building blocks for more advanced programming tools like data structures. So therefore, it's very important, especially if you are computer science, computer engineering, or even electrical engineering, you want to make sure that you understand linked lists and pointers very, very well. So let's go ahead and introduce linked lists. And one thing you'll notice in this video and in many of our examples is we are going to be drawing a lot of pictures. So make sure you draw pictures to help visualize what is going on. Many students find linked lists a little bit tricky to learn at first because there's a lot of new syntax and there's important rules that you need to follow. But by drawing pictures, it makes it much easier to understand what's happening. So please take the time to draw pictures to help understand all the new rules and important details of linked lists. So often people like to use analogies when describing linked lists. Some like to compare linked lists to a train or a caterpillar, and that's because linked lists are made by connecting multiple nodes together. Just like how a train has an engine and multiple train cars connected to each other, a linked list has a head pointer and that pointer connects each node in the linked list. So notice, each node of a linked list is a struct or an object, and then of course they are connected by pointers. So each node must contain some pointer, often called next, which points to the next item in that linked list. Notice that the head pointer will always point to the first node of our linked list, and our very last node's pointer will point to memory address null, or memory address 0. Sometimes, just like with pointers, we also write the null address as null pointer. So notice for linked lists, we use nodes to define the pieces of our linked list. And so in order to create our linked list, we first must create the nodes. And we need to declare and define what our linked list contains. So a node can be either a struct or an object made from a class. And a node always needs to contain the following things. First, a node must contain one or more pieces of data. For example, we can have an int variable named data as part of our node. Notice you can have more than one bit of data inside your node. You could even have arrays or other items stored in there. And so you have to have some data that is stored in your node. And then, in order to link your nodes together to form your linked list, you need to have a pointer. So notice in this case, we named our node list node. So in this case, we're using the list node struct as a template, or as basically the blueprint for the nodes of our linked list. And remember, the pointers need to connect one node to another. And so in this case, the pointer is of list node type because it needs to connect one node to the next. And often we do name our pointer next. So that way it's very clear that our node contains some bit of data that we want to store, and then a pointer which will connect us to our next node. So one of the first things that you'll want to learn for linked lists is how to build a linked list. And when you first see this process, it might appear intimidating and kind of complex. My biggest recommendation is to follow along with me as you draw pictures to visualize each step of this process. Drawing pictures really helps break this process down into simpler chunks. So here, very briefly, we'll review this process step by step, and then we'll go through one step at a time, draw pictures, and look in greater detail at this process one step at a time. So our first step is to declare a struct or an object, which we want to use as basically the template for each node. So we have to declare what each of our nodes looks like. We probably want our node to contain some data, and then we also want our node to contain some pointer, such as next, which would point to the next node. Remember, it is possible to have multiple pointers and multiple pieces of data within each node, but for our purposes, we're keeping things simple, and we're just learning about nodes that contain one piece of data and one pointer. The next thing to do is to declare a pointer which points to the head of the linked list. So we often call this pointer head. Because it points to the front of our linked list. Our next step is to take our head pointer and use the new operator to make head point to a new node. For example, we can write the code head equals new list node. If we had declared that list node struct on our previous slide, with an int data and a list node type pointer next. Notice if we say head equals new list node, that will make our head pointer point to a new node or a new struct of list node type. So notice in this case, now our head pointer is pointing at a list node struct created in the dynamic memory. Finally, we need to update the data inside of our new node. And we'll use what's called the arrow operator to update the data and the pointers inside each node of our list. And once we've created that first node, we can keep adding nodes to it. So it turns out we can take the pointer in our first node and make that pointer point to a second node. And make that pointer point to a third node if we so choose. And we can grow our linked list in the dynamic memory until our linked list has reached its desired size. Finally, one last important practice we follow is, for our class, we are making just simple linked lists, so we want to make sure the very last node of our list always points to null. In more advanced courses, you might make different kinds of linked lists and data structures where the last node points somewhere else. All right, so once again, for our purposes, we want to make sure that our very last node always has its pointer pointing to the null pointer, or null. That way, we always know where the end of our list is. We'll see later on that we can use a while loop and search through our list until our pointer points to null. That way, we always know where the end of our list is located. Okay, so let's now go through the steps one by one and review in greater detail how we complete that process for building a linked list. So as mentioned, our very first step of creating a linked list is to first declare a struct or object. Basically, we need to figure out what do we want each node of our list to contain. So in this case, in our example here, we have declared a struct named listNode. So this is just one example, but you see the listNode struct contains some int value named data and a listNode type pointer named next. This pointer will only be able to point to a listNode struct. And so we use this pointer to connect to the next node. It's much like connecting train cars or connecting different pieces together. This next pointer allows us to connect this current listNode struct to an additional struct. One important thing to note about this step is we are not actually creating any nodes just yet. All we are doing is making a declaration for the listNode struct. So we're basically just telling our compiler, if I declare a listNode type struct, this is what each listNode contains. So all you're doing is saying what each node of your linked list will look like. In this case, I want to build a linked list of listNode structs, and each listNode struct will contain some int variable named data, and then a pointer called next. Remember, you definitely need to have that pointer in there because that is the thing that will allow us to connect to another node and create our linked list. All right, so our first step was to declare the node that we wanted to use. Our second step is to declare a pointer which points to the head of the linked list. So remember, this pointer needs to point to the same type of data as our node. So in this case, if I'm using listNode structs, then our pointer needs to be listNode type. So we see in this case, our head pointer for our example needs to be a list node type pointer. So to declare and initialize our pointer, we use the code list node head equals null. So what this is doing is this is creating a pointer named head and making it point to the null memory address, where head is a pointer of list node type. Notice the head pointer is not a node itself, it's just supposed to point to the very first item in our list. And very often, programmers generally call the pointer head because this is the pointer at the very beginning of our linked list. And most of the time, if we have an empty linked list, we follow the practice of making our head pointer point to null to indicate that the list is currently empty. So right now, we don't have a full linked list yet. We just have a pointer that currently points to null. All right, so let's take a moment and review what we have so far. Our first step was to declare that list node struct. Our second step was to declare our head pointer and make our head pointer point to null initially. In our third step, we want to take our head pointer, and instead of having it point to null, we want to make our head pointer point to a list node struct. So here we are making our head pointer point to a dynamic list node struct. And this list node struct will be our first node in our linked list. Notice that we need to use the new operator because we're working with dynamic memory here. Also notice that there is no index. The only way that we can access this list node is by using our head pointer. And this is a general theme that you're going to see with linked lists, is that the only way to access the data in our linked list is by using pointers. So we write the code head points to new list node. That is going to create a new list node struct in dynamic memory and make head point to that memory address. Notice how we drew pictures here. We have our pointer head, I drew an arrow, and then I have a box that shows data and next. This is to match our list node struct, which contains an int variable data and a list node type pointer named next. So drawing these pictures can really help visualize what's happening when we write this code. All right, so we have just created our very first node of our linked list. Now we need to initialize the data inside that first node so that it contains whatever data that we want to store. So how do we do that? That brings us to step 4. In step 4, we need to use this operator. It's actually called the arrow operator. And we will use this to assign values to the data and next inside our list node struct. So remember, currently we have an empty list node struct, which contains an int variable data, and some pointer next. So remember, this is a list node struct. So using the tools we already know, what we would need to do is we'd need to use the asterisk in order to go where head points, and then we'd use the dot operator, and we could say, for example, asterisk head dot data equals 23, and that would put 23 there. We could write asterisk head dot next equals null, and that would make us point to null. So you could write code like this and it would be valid and it would be correct, but this is not what programmers typically do. People decided that it's too much of a pain to write asterisk head dot data or asterisk head dot next. So instead of doing this, we instead use what's called the arrow operator. We see that the arrow operator is a faster, easier way to write an equivalent expression. So instead of writing asterisk head dot data equals 23, we write head arrow data equals 23. This basically says, go where head points, and set data to 23. Head arrow next would tell us to go where head points, and set next to null. So the arrow operator is a very powerful tool, very powerful shortcut. And as you see, it combines the actions of our dereferencing operator, or asterisk, with the dot operator. And so when manipulating linked lists, it's very important that you understand how to use the arrow operator. It's a very important tool that we will use throughout this course. Alright, so now we know how to use the arrow operator in order to update the data stored in our linked list. So now all that's left is to use the arrow operator to update data in our list and keep adding nodes until we have finished creating our linked list. Here's an example. So at the end of our step 4, we had our first node of our linked list. And we had just initialized the data value to contain the number 23 and next to point to null. But notice what I can do. Instead of making this next pointer point at null, I can write the code head arrow next equals new list node. That's going to take this next pointer, go where head points, find our next pointer, and make that next pointer point to a new list node struct. So notice this allows us to add a second node to the end of our list. And now, just like before, I can use the arrow operator to update the data and the next pointer in that second node. Notice in this next line of code, I write head arrow next arrow data equals 24. This is the same as writing go where head's next pointer points, and we will set the data value to 24. So notice I go where head's next pointer points, that's my second node, and I set my data value to 24. Finally, I want to make sure that the end of my list points to null. So notice I write this additional line of code. Head arrow next equals null. This will make us go where head's next pointer points. And make that next point to null. So we go where head's next pointer points, that's our second node. We make the next pointer point to null. Notice how powerful the arrow operator is here. With just 3 lines of code, I was able to add a second node to the end of my list. Here's an example of how we could add a second node to the beginning of our linked list. So all we would need to do is first create our new node that we want to add. So what we did here is we created a completely separate pointer named newHead. So we created this newHead pointer, which can point to list node type structs. Then in our second step, we made newHead point, make newHead point to a new list node type struct. And finally, in our third step, look what we did. We took newHead's next pointer and we made it point to head, or we made it point to the node which we wanted to insert in front. So our end result is that we have inserted that new list node our new list node struct at the front of our original head linked list. So notice now we have newHead and next attached to our old linked list containing our head pointer, which is still pointing to that node that contains 23. So there's one last step that we would need to do in this case. When working with linked lists, we always want our head pointer to point to the very first node of our linked list. Here, our head pointer is pointing to the second node of our linked list, which is not correct. So finally, our last step is to update the data inside of our new node, and then we update our head pointer to point at the beginning of our list again. In this case, the beginning of our list was where newHead pointed. So we wrote the code head equals newHead to make our head pointer. Originally head was pointing at our second node, and we change it. So now head points at the very beginning of our list. All right, finally, our very last step is to make sure that the last node of our list always points to null or null pointer. You may learn other rules in more advanced courses, but for our purposes, we want the very last item in our linked list to have its next pointer point to null. This way, we always know where the end of our list is located. Alright, so I realized that linked lists can be tricky to learn. The best way to get better at linked lists is by drawing pictures and practicing examples. So for the rest of this video, we're going to practice some examples. And you may be asked to do something similar in our assignments. So definitely, please make sure you take the time to follow along with these examples and practice drawing pictures. Drawing pictures truly helps, and it will make it a lot easier to understand linked lists. So let's go ahead and go through these examples and practice really understanding what's going on in these bits of code. So in our first example here, we are asked to draw what the code produces and explain your answer. So this first bit here is actually not really producing anything. Here we are just declaring a list node struct. And we know that each list node struct will have some int variable named data. So I'll just call this data, where there's an int sized space. And then we have a pointer named next, where next is a pointer of list node type. So in this case, this is just a declaration so we know what a list node type data is. In this case, a list node struct contains a pointer next and an int type value data. So first bit of code is just a declaration. It's not actually producing anything yet. But what happens here? In the second line of code, we are declaring a list node type pointer named head, and we're making head point at null. So if I were to draw this, we could draw something like this. In this case, this is the very first step of creating a linked list. Remember, we need to declare what the nodes of our linked list look like, and then we need to make a pointer that will point to node type data values in order to connect and create nodes of our linked list. Let's try our next example. And please draw along with me as we go through these examples. By drawing pictures, you'll build a much better understanding of how linked lists work. So in example 2, we are told that we currently have that pointer named head that we just declared in part 1. So we have this. And we should also assume that the list node struct is also declared. So let's go ahead and write that. We'll assume that the list node struct is also declared. All right, so we have that head pointer of list node type currently pointing to null. Then the following code is run. First, we have head equals new list node. Well, that is going to make our head pointer point to a new list node struct in dynamic memory. This creates the first node of our linked list. So after that head equals new list node runs, now head points to a new list node struct with uninitialized values for data and next. What does this second line of code do? Head arrow data equals 12. Here we're using the arrow operator to initialize the data where head points to 12. So we go where head points, and we update that int value data to be the value 12. And finally, in our last step, we're using the arrow operator to make our first node's next pointer point to null, or a null pointer. Remember, we always want the last node in our list to point to null, so we know where the end of our list is located. So finally, after all of that code has run, we have our head pointer pointing to just one node containing the data value 12 and having its next pointer pointing at null. So we have just created the first node of our linked list. Let's now try example 3. In example 3, we are given that we already have this list initially. So we already have a linked list of list node type. So we can also assume that our list node struct is declared. And look what's happening next. First line of code, list node star next node. Well, what would that do? That's declaring a pointer called next node. So declaring a list node type pointer named next node. So if I were to draw that, I'm basically just drawing next node. Currently, next node is pointing to nothing. But look what happens in our second line. Next node equals new list node. Here, we are making next node. Remember, we're a list node type pointer. We're making that pointer point to a new list node struct. And remember, every list node struct contains some int value data and a pointer named next. What does this line do? Next node arrow data equals 99. This is going to update the data where next node points to be 99. So next node is pointing at this whole struct, so we're going to go to data and update the value to be 99. Finally, we have next node arrow next equals null. This will update the next pointer where next node points to point at null. So notice, these first 4 lines of code have basically created a new node where next node points. And we initialize data to 99 and made next point to null. All right, well then what's going to happen here? We're saying head, arrow next, arrow next, arrow next. We're going to make that point to next node. So here we're going to go where head, arrow next points. So head, arrow next points at this node, and make that next pointer point where next node points. So instead of pointing at null, look what just happened. Essentially, this code connects the third node of heads list to our new node where next node points. And finally, our very last statement, see out head, arrow next data. Well, this is going to go to the 1, 2, 3. It's going to go to the 4th node. This is where head, arrow next points, and output the data value to the screen. So what value will we output if we go to our 4th node? Well, our 4th node contains the value 99, so this will output 99 to the screen. So therefore, this code produces a 4-node linked list and the code allowed us to add the node containing 99 to our list. Notice how helpful these pictures are for visualizing what's happening. I highly recommend that you take the time to go through these examples and make sure you really understand what each line of code is doing. It's really important that you understand the arrow operator and how to create and manipulate these linked lists. Let's do one last example. In this case, we are asked to write the code which will add a node containing the number 99 to the end of the list. Here we can assume that the list node struct is declared. How would we write this code? Actually, it's the same code that we had just looked at in the previous example. The first step we need to do is to create a new node containing 99. Then we need to make the third node in heads list point to the memory address of the node containing 99. So let's go ahead and give this a try. First, we need to create that new node. So to do that, let's go ahead and create that pointer. So we have, first we need to declare a pointer new node. Then we can say that new node equals new list node. So here we are declaring a list node type pointer. And making that pointer point to a new node. Then all that's left is to initialize that new node and then attach it to our list. So we can say new node arrow data equals 99. New node arrow next equals null. So basically, this code has allowed us to create a pointer new node that contains the data value 99, and then next is pointing to null. Finally, our last step is to connect. We want to attach this node to the end of our list by taking our third node in heads list and making this next pointer point where new node points. So all we need to do is rewrite head arrow next. Head arrow next gives us this location. Head arrow next arrow next head arrow next would give us our second node, right? Because head arrow next points at second node, head arrow next points at the third node. We want head arrow next next value. I'm going to take this next and make it point where new node points. So this code will make head's third node next pointer point at our new node. or basically point where a new node points, and this attaches new node to our existing 3-node list. All right, so feel free to reach out if you have any questions about these linked list examples that we've covered so far. Definitely make sure you understand the arrow operator and go back through our examples if you need some more practice. Before we end for today, let's cover some linked list good practices and go through an additional example. We will also have an additional video covering more detailed operations with linked lists, so be sure to check that video out as well. Here's a few very important linked list good practices that you'll definitely want to know. All right, so our first good practice is to make sure you check. Make sure your list is not empty before manipulating it. So often to do this, we'll use an if statement, such as if head For example, if head points at null, then we know our list must be empty. We don't want to try to manipulate an empty list, because if we try to manipulate data at memory address 0, we're going to get a runtime error. So you'll notice in our example code, we often include if head double equals null pointer to double check and make sure our list is not empty before trying to do stuff with it. Another good practice is to always keep a pointer variable pointing to the head of our linked list. And most of the time, we tend to call that pointer head because it's pointing to the front of our list. And we'll see later that we use that pointer in functions and also to access the data. And so it's also very important that you do not lose access to your head node, or to the very first node of your list. If you overwrite that pointer, you're going to lose the ability to access your entire list. And so these are called lost nodes. Lost nodes are nodes which can no longer be accessed using pointers. And the problem with the lost nodes is that they're going to sit there in the dynamic memory until your program ends. And we have no way to delete them because we no longer have a pointer pointing at them. And if you've ever worked with a very buggy program that crashes after it's run for so long, you may have run into a program that produces lost nodes. Lost nodes create something which is called a memory leak. So let's briefly cover memory leaks. If we have a lost node, see how sad this node is? It's lost. There is no pointer is pointing to this node. So the problem with the lost node is that we are unable to access the node, nor can we delete it. Sometimes these nodes are called orphaned memory, because they're abandoned and we're unable to access the node and include it in our program. So these nodes will just be sitting in our memory, potentially clogging up our memory and eventually causing the system to crash when we run out of memory that we can use. So it's very important when working with linked lists, you always need to keep some pointer pointing to the head of the linked list, and you always need to maintain some connection to your nodes using pointers. Because otherwise, you will end up with some lost nodes which can no longer be accessed, and they'll just be sitting there clogging up data until our program crashes or closes. So make sure you remember, always keep some pointer pointing to the head or to the front of your linked list, and always make sure each node is connected to the others using pointers so that you don't lose access to any of your nodes. The last thing you want to do is create lost nodes and orphan memory and cause your program to crash. All right, so for the purposes of our course, we want to make sure everybody knows the following basic operations for linked lists. So in today's video, we've covered this first operation, which is adding a node to the end of our list. We also know how to add a node to the front of the list. Next time, we're going to take a look at some additional operations, including inserting a node within a list, going through our linked list, deleting nodes, destroying the entire list or a single node, and also searching in a linked list. So real quick, before we end, let's cover one last example. So in this example, what we're going to do is we're going to declare and create a linked list class. And this is just an example of how we can use what we've learned about nodes and classes to create some nice data structures. So here's an example of our linked list class. Notice we call it int link list because it contains a node struct and each node holds a single int variable and a node type pointer so that we can connect to additional nodes and create a linked list. And notice that we also have functions. Notice here the add function will add a node containing element to the beginning of our list. We also have a remove function that will delete an element from our list. So if we want to remove an element that contains, like number 2, for example, this would find the element containing 2 and remove it. We also have a contains function that will return true if some int value element is in our list. Notice that we've also set up this class so that head and length are private variables. So the head pointer of our linked list cannot be directly changed. We're able to better protect that data. And the length variable allows us to kind of tally how many nodes that our linked list contains. So in our next class, we'll take a closer look at how we would actually write some functions in order to fully implement this linked list class. For example, you can see we have this add function. And notice what the add function will do is it first creates a new node. So we're creating a new node struct, which contains some data and some next pointer. We make next point to null temporarily, and we update data to contain whatever element was given in the argument. And then all we do is we add the new node to the front of our list. So if we have some existing lists, notice what we are doing. We take node arrow next, and we connect node's next pointer to where head points at the front of our existing list. And then we update our head pointer to point at the front. And so by doing this, we were able to attach that new node to the front of our list. And notice we do what's called bookkeeping. We have also incremented our length variable to keep track of the number of nodes in our list. Since we added this new node to our list, we have to increment our length value so that we have an accurate number of nodes that are present. Finally, we can also write main functions in order to test out our linked list classes and also add and remove items. If you're curious, I recommend that you try implementing this linked list class and start playing around with some of the functions in it. We'll take a closer look at this in our next video. Alright, so let's go ahead and wrap up here for today. You should now have a better idea of the advantages and limitations of linked lists. Remember, our goal at the end of the day is to have a toolbox full of different tools that we can use for different kinds of applications. We learned that linked lists are really useful if you want to be able to easily insert and remove data anywhere in your list. However, one disadvantage of linked lists is that we lose the ability to do indexing like how we do it in arrays. So we're not able to go directly to an item of interest. Instead, we have to step through node by node of our linked list until we find the thing we want. So it's important to remember these advantages and limitations when designing the right data structure for our programs. Finally, please also start drawing pictures and getting comfortable writing code to construct linked lists. Drawing pictures really helps, so please draw pictures to help understand what's going on. And we'll continue drawing pictures in our next video as well. Finally, make sure you understand how to use that arrow operator to manipulate linked lists. Remember, the arrow operator combines the dereferencing operator and the dot operator. So it's a really convenient and important tool to know. Thanks everybody for joining the fun and watching today's video. Please do check out our next video for additional review of linked lists. Thanks everyone for joining the fun, and we'll see you in the next video.